Okay, so our final talk today is by our own Golowich, who will tell us about transversal CCZ gates.
Thank you. Yeah, so today I'm going to be talking about quantum LDPC codes with transversal CCZ gates. This is based on joint work with David Lin, but I'll also, as part of this talk, just try to give an exposition of kind of the techniques that have been used recently in the last couple of years, the literature, and kind of trying to give a unified framework for kind of all of the results and the state of the results that we've seen. So the motivation for this problem comes from like a very practical problem in fault-tolerant computation. This is just the problem of performing fault-tolerant non-Clifford gates. And we heard a lot about this on Monday. So non-Clifford gates, such as like the CCZ gate or the T gate, are necessary for universal quantum computation. If you just have Clifford gates, you can simulate that efficiently in polynomial time with a classical computer. But if you add a single non-Clifford gate, you all of a sudden can do universal quantum computation. And so perhaps unsurprisingly, these non-Clifford gates are also some of the hardest things to render fault-tolerant. And so they're often like a major bottleneck, sometimes the primary bottleneck in schemes for quantum fault tolerance. Quantum LDPC codes are quantum error correcting codes that are defined to be decodable via local measurements, meaning you can perform a bunch of measurements to like a constant number of qubits at a time within your constant number of physical qubits at a time within your physical code state, and then you can combine these measurement outcomes and correct whatever error occurred on your code state. And so the fact that all these measurements are local means that these codes are ideal for fault-tolerant quantum computation, because each measurement only touches a constant number of qubits, so you can perform it without propagating errors more than a constant amount, which means that you can essentially correct, if the code has good enough parameters, you can correct more errors than you cause during the error correction, and overall you gain when you do this error correction. You suppress errors more than you introduce errors. So the focus of this talk is combining these two things, asking how can we efficiently and fault-tolerantly perform non-Clifford gates on the logical data encoded in quantum LDPC codes. And as I mentioned, these quantum LDPC codes, they're also very practically motivated. I think most, if not all, fault-tolerant schemes that are being looked at for use in practice on real quantum computers are to some extent based in quantum LDPC codes. And so this talk does have like a very practical motivation, which again, we heard a lot more about on Monday. And specifically, we'll be looking at ways to do what are called transversal CCZ gates. So these are, for the purpose of this talk, just any constant depth physical circuit that you can apply to a physical code state of your LDPC code, such that when we apply this constant depth physical circuit, it induces logical CCZ gates on the underlying message encode inside our code. And this constant depth property means that the transversal CCZ gate is both very efficient, it only requires constant time overhead, and it's fault tolerant because constant depth circuits have constant size light codes, so they also can't propagate errors very far. So these transversal CCZ gates are really kind of this highly desirable object that we want to construct for our quantum LDPC codes.
As being tensor product states, is this consistent with that definition?
Sorry, transversal single qubit gates are?
Like you just need to apply a gate on each line to apply like a T for the state.
Oh yeah, so this is, right, so this is similar. I guess here we have now a 3 qubit gate instead of a T gate. And so I guess what you said is like a depth 1 circuit.
Yeah.
Yeah, so I'm saying constant depth, so though actually all the codes we'll talk about, you can perform some like kind of local unitary, like some kind of do a bit of concatenation and get it down to depth 1. So it's basically the same, though for the presentation, it's a little easier to describe it as constant depth circuits.
Okay.
Thanks for the question. Great, so just a brief recap in case you're not familiar. So the CZ gate is like a baby version of CCZ. It's actually a Clifford gate which just takes in like 2 qubits, x, y, and introduces a phase of -1 if both x and y are 1. Otherwise, it does nothing. And CCZ is a non-Clifford gate. It does the same thing but to 3 qubits. It flips the phase if all 3 are 1. If any of them are 0, it does nothing. Great. So hopefully I've now convinced you, or maybe the talks on Monday convinced you, that this question of transversal non-Clifford gates is important. From a practical perspective, I'll now try to convince you that it's also very interesting from a purely theoretical perspective. And the way I'll do this is I'll give a topological interpretation of the entire question. So quantum codes in general encode some number k of logical qubits into some number n of physical qubits, such that if we corrupt up to some number d of the physical qubits, we can run a recovery map and recover the original message. So in general, we can view quantum codes as topological spaces, such as a 2-dimensional torus for the 2D toric code or a 3-dimensional torus for the 3D toric code. Here, this cube represents a 3D torus, so we should imagine it has periodic boundary conditions. And the length of the code corresponds to the number of cells, such as edges or faces, at a given level or at a given dimension in some tiling of this topological space. So for instance, for the 2D toric code, we take a 2-dimensional torus, like the surface of a donut, we tile it, and then we place a qubit on every edge. For the 3D toric code, we do the same thing for a 3D torus. We now place a qubit on every square in our tiling. Then the k logical qubits correspond to intuitively like non-trivial cycles in this topological space. So for instance, in the 2D toric code, we kind of have 2 non-trivial cycles. We have like a cycle that goes around the torus this way and one that goes around the other way. And by non-trivial here, I just mean that you can't fill in the interior of the cycle, or this cycle is not the boundary of any region within the topological space. So you could imagine like we take a very small region of the torus and take its boundary, and it'll be like a really small loop on the surface of the torus. We won't count that as a non-trivial cycle. That will be like a trivial cycle. Similarly, the 3D toric code has 3 non-trivial cycles corresponding to these, or at least 3 non-trivial cycles in 3 non-trivial 2-dimensional cycles, corresponding to like these 3 membranes going in the 3 different directions in the picture drawn here. And the distance d, or the error resilience of our code, corresponds to the minimum length of any of these non-trivial cycles. Great, so this is like the standard view of a quantum code as a topological space. And I'll now describe how transversal CCZ fits into this picture. So for simplicity, let's just imagine we're trying to do transversal CCZ across 3 different code states. So we have 3 code states, and we want some constant depth circuit of physical CCZ gates to induce, such that when we perform these physical CCZs, it induces logical CCZs on our underlying messages across the 3 code blocks. This was our definition of a transversal CCZ gate. It turns out that on the topological side, this corresponds exactly to having a triple of cycles that intersect at an odd number of points, such that this intersection number, the parity of this intersection number, is robust under local perturbations. So what do I mean by that? If you look at the 3D toric code, these 3 membranes, these 3 non-trivial cycles I've drawn, they intersect at a single point. And even if we perturb any one of these cycles a little, maybe we like shift one of them to the side, they'll still intersect at a single point. We could perturb it in a little bit of a crazier way and get like 3 intersection points, but we'll always have an odd number of intersection points. And yes.
Can you do logical CCZ within the same block? Let's say any triple in K?
Yes. So for the 3D toric code, you can do that. It ultimately will follow from similar reasoning here, but I think it's just easier to think about having 3 different code blocks.
Okay. But you're gonna talk about like exactly the same thing for LDPC, right?
Yeah.
Okay.
Yeah, for like more general. So this is an LDPC code, but we're going to try to get like better LDPC codes with better parameters. Great. Oh yes.
You say cycles here, you mean these membranes?
Oh yeah. Yeah, sorry. So I haven't yet defined cycle, but yeah, I mean like, yeah, you can think of it as like a surface or a submanifold or like a membrane.
Is it easy to see or explain how you get them to intersect at more than one common point?
Well, like how could they intersect at 3 points?
Yeah.
Yeah, so one stupid thing you could do is like, so the deformations we're allowing here are like, we can add in the boundary of any small region. So we could just take a small sphere and add in the boundary of that to one of these cycles. And so then if we take the intersection of two membranes, we get a line. And so then if we add a small sphere, we can get two more intersection points. Great. And so the like algebraic name for kind of this robust intersection number is the cup product. And kind of the whole story of this talk will be kind of generalizing this cup product from manifolds to these more exotic topological spaces that correspond to good quantum or better quantum LDPC codes. Cup? I do not know. I mean, we draw it as a cup. Yes.
Does this topological space picture still hold for like CSS codes, or is it not as clear in that case?
Yeah, so actually everything we'll talk about is basically CSS codes, which you can also view as like cochain complexes.
Okay.
For more general codes that aren't CSS, I'm not so sure.
Okay.
But for CSS codes, yeah. Great. So just to recap, our goal on the practical side was to construct quantum LDPC codes with large distance and large dimension, exhibiting transversal CCZ. On the topological side, this corresponds to constructing topological spaces with a lot of large cycles, large non-trivial cycles, exhibiting these robust intersection numbers, or this cup product. So it's like we have this like practical error correction question on one side, and on the other side we have a like topological question, which I think is quite interesting on its own right. And somehow these seem to be the same question. So how well can we do right now? What are like the best parameters that are known? So I guess for a long time, the best known parameters in most regimes were just given by the three-dimensional toric code. Or if you've heard like the 3D color code, I think it's basically isomorphic to the 3D toric code. So this is a code of length n. It encodes just a constant number of logical qubits, and it has distance roughly n to the 1/3. Then this is actually the state of the art in most regimes, as far as I'm aware, until last year, when we got this construction with David Lin of codes of length n, dimension n to the 1 minus epsilon, and distance roughly n to the 1/3. So these weren't quite LDPC. They had like polylog locality instead of constant locality of the stabilizers. But you can see we basically took the 3D toric code parameters and basically preserved them up to polylog factors, except we increased the number of logical qubits from like a constant up to almost linear. It's like n to the 1 minus epsilon. So we got like a significant improvement in the rate of these codes. And then just last year, Guanyu Zhu had this very nice construction that actually was the first one to break the n to the 1/3 distance barrier for LDPC codes with transversal CCZ. He got codes of both dimension and distance square root n. And if you read kind of these, I guess the paper, so as far as I know, these last two basically cover the best known parameters in basically all regimes that I'm aware, or at least in most regimes, maybe not in like the very low distance regime. So this, all right, so if you read kind of these three papers, they're all kind of presented in a different way. Like, I guess Baumann came with this 3D color code a while ago. Guanyu's paper was presented in terms of like turning LDPC codes into manifolds and so forth. But in this talk, I'll be showing how like these all basically use the exact same framework for constructing these codes. And yes. Oh, it's an arbitrarily small constant. The polylog depends on that. Like the polylog will become a worse polylog as epsilon gets smaller. Thanks. So yeah, so the the framework I'll be presenting here is kind of like a unification of some frameworks presented in the last couple of years, like one by David Lin, a nice one by Nico, Margarita, Jens, and Nat. And also this will, it's also like somewhat inspired by Guan Yu's papers.
These codes come with efficient decoders as well.
So the toric code definitely does. This one, I'm not 100% sure. It would have one, except that it is polylog locality. So I haven't worked out if kind of like a lot of time these decoders do a brute force search in a local neighborhood. So you would want to optimize that a little because brute force on a polylog is a bit expensive. And I'm not sure for Guan Yu's, but it probably does, I think. Great. So I'll now get into the technical details. I'll give a bit of coding theoretic background. Then I'll try to provide like a more detailed explanation of the toric code and then explain how we generalize that to better QLDPC codes. So in brief, a classical linear code is just a linear subspace of an n-dimensional vector space over F2. And this is a length n linear code. And the code is LDPC if it's the kernel of some parity check matrix H, such that every row and every column of H has constant Hamming weight, or has a constant number of non-zero entries. Then a quantum CSS code consists of a pair of classical codes, QX and QZ, such that the dual of each of these codes lies inside the other one, where the dual is just the set of all vectors that are orthogonal to everything in the code. And if you haven't seen quantum CSS codes before, you should think of them really as like kind of coset codes or quotient codes. You should think of the CSS code given by QX and QZ as like the quotient QZ mod QX perp. And so like this quantum CSS code will have length n. The dimension will be the dimension of this space QZ mod QX perp, which is just the dimension of QZ minus the dimension of QX perp. And the distance will be the minimum Hamming weight of any element of a non-trivial coset in either QZ mod QX perp or in QX mod QZ perp. And also the code space of the CSS code consists of the span of all uniform superpositions over the elements of any coset in QZ mod QX perp. And then the code is LDPC if both QX and QZ are LDPC. So they have constant weight parity checks. Great, so what are transversal CCZ gates in this language? If we're given some set of triples of physical qubits, so P is just a set of some subset of n cross n cross n, then we can imagine doing a physical gate where we just perform physical CCZ on every triple of qubits inside the set P. And if, for instance, it's shown in the top right, if P is like this set of 1, 1, 1, 2, 4, 3, and 5, 2, 4, we just do CCZ on the first qubits of 3 successive code blocks on qubit 2, 4, and 3, and then we do a CCZ on qubit 5, qubit 2, and qubit 4. So P just says which physical qubits, triples, do we do a CCZ on? And when we do these CCZ gates, what actually happens is we just flip we apply a phase -1 to the f sub p of ABC for a computational base state ABC, where f sub p is just this trilinear form that just adds up over all triples in P, all triples Hij and P of AH, BI, CJ. So I've just like literally taken the definition of a CCZ gate and wrote down what the phase it induces when we apply it to a state ABC. So we want kind of circuits of this form, like of physical CCZ gates that preserve the code space, which will correspond to like transversal CCZ gates. And this the physical action of CCZ on these triples P will preserve the code space if this trilinear form FP is QX perp invariant. And by that I just mean that kind of FP, the value of FP is invariant on cosets of QX perp. Or FP of any 3 inputs where all of them lie inside QZ and at least one of them lies inside QX perp equals 0. So this is what we call QX perp invariance. If FP is QX perp invariant, then this physical CCZ gate on all triples in P preserves the code space, so we can say that this is like a transversal CCZ gate, as long as it's a constant depth circuit. So our key challenge will be to construct codes that permit QX perp invariant trilinear forms FP. And it'll sometimes be helpful to kind of talk about just the CZ case. Of course, we want this to be constant depth, right? So it'll sometimes be helpful to talk about just the CZ case, because it's, I guess, easier to draw 2 things and 3 things, and all these definitions go through for CZ as well. Great. So before going into exactly how we construct these kind of QX perp invariant bilinear forms, I'll just kind of briefly recap this proof that QX perp invariance implies transversal CCZ, or specifically implies transversal CZ. And the reasoning is that to preserve the code space, we just want to make sure that kind of every pair of code states, and a pair of code states looks like this. It looks like the sum over all ST in QX perp of ket A plus S and ket B plus T. We want all terms in this sum to receive the same phase, because that means that this entire sum under our physical gate is mapped to some other code state. So that basically just means that we want FP of A plus S comma B plus T to have the same value for all S and T in QX perp, which is literally just the definition of QX perp invariance.
Right, and this is only the fact that this transversal physical operation acts logically on the code.
Yeah.
It doesn't say anything about what it does.
Oh yeah, so that's a great point, yeah. Yeah, so it is really important to analyze what it does. Unfortunately, in this talk, I won't have a chance to get into kind of how we control that. But yeah, that's actually one of the most important things, because it's much easier to write down circuits that look like they act non-trivially, but when you look at what it does to the code, it actually does nothing. Great. So I'll now try to give a few more details on the kind of the 2D toric code. And specifically, I'll try to give you like a proof that the 2D toric code supports a transversal CZ gate. And if you just take this exact proof and kind of just move it up 1 dimension, you get like an airtight proof that the 3D toric code supports a transversal CCZ gate. And then this is really the fact that we're going to be trying to generalize to better LDPC codes. And the nice thing is this is kind of we can see it pretty visually. So if we take a 2D toric code and we kind of cut it open and lay it out just on a surface with periodic boundary conditions. So the qubits correspond to edges. Our code QZ in our CSS code for the 2D toric code just consists of cycles. So here's an example of a cycle. It's just the code word that is 1s along this orange cycle and 0s everywhere else. And then QX perp corresponds to boundaries of squares, or it's the span of all the unit squares in this lattice. So for instance, the vector that's just 1s on, like 4 1s in this square and 0s elsewhere is an element of QX perp. And if we take 2 copies of this 2D toric code and just lay them on top of each other, but with a small offset, this offset's going to be really important, then we can define a set P corresponding to the physical CZ gates that we do, where P consists of every pair of edges, 1 black and 1 gray, so one from one of our 2 copies of the code, one from the other copy of the code, that intersect at a point. So here it's like a 5x5 square, so we're going to do 25 physical CZ gates corresponding to like every intersection you see between a gray edge and a black edge. And if we now look at any cycle on our first code and say any boundary, so any cycle A on our first code and any boundary S in our second code, then by definition, FP of A comma S is the number of points, mod 2, where the support of A intersects the support of S. And you can see that this will always be 0. So why is this always 0? Well, in this picture, it's 2, which is mod 2 is 0. And in general, if you take a square and then have any cycle in the plane, this cycle can't enter the square without leaving the square, because it's a cycle. So for every time this cycle enters the square, it'll also leave the square, which means that the number of points at which this cycle and this square intersect is going to be even. So that means that fp of AS is 0. So fp is indeed QX perp invariant by definition. In other words, the 2D toric code supports transversal CZ.
Excuse me, sorry, I'm gonna ask the same question again. So how do you do Control Z in the same copy, not two copies?
Oh yeah, so you still do this thing where you take the code and then shift it a little bit, and now you get a bunch of intersection points. But now we just imagine that like the qubit on like each of these edges is the same as a qubit on this edge. And then you get a well-defined CZ circuit acting within a code block. For instance, you'll get like a CZ between kind of, so we have an intersection here, so that corresponds to a CZ between like this qubit and this, which is the same as this qubit. So if we just imagine these are actually the same code, but otherwise we do the same thing.
Thanks.
Great. So this is how we get transversal CZ on a 2D toric code. The topological view of this is that every time we add an element of QX perp to some cycle, so we add some square to some cycle, that's literally just doing a local perturbation of a cycle. Like if we have this cycle in orange, then we imagine adding in like this square, that will just kind of locally perturb the cycle it'll reroute it to instead go up here instead of down here. So what this says is that QX perp invariance is really just the same thing as having a robust intersection number, meaning robust with respect to these local perturbations that we get by adding boundaries or adding squares. This is kind of this topological picture that I mentioned at the start of the talk.
But it had a whole bunch of cycles still.
Oh yeah.
Intersection property.
Yeah, sorry. So by local I meant like you only can shift it like you can do arbitrarily many of these local perturbations, but you can never like add in a non-trivial cycle. So at any given time you can't do something global. But yeah, it's like we're adding in any number of perturbations, but each one is local. Great. So to summarize, we've just seen a proof that the 2D toric code supports transversal CZ because every cycle and every boundary intersect at an even number of points. And basically the exact same reasoning you can just go through in the three-dimensional case to show that the 3D toric code supports transversal CCZ because every pair of two-dimensional cycles, meaning like two of these membranes, and a boundary, meaning like a little sphere or a little cube, will also intersect at an even number of points. Essentially here it's because two membranes intersect along a 1D cycle, and then every 1D cycle or every curve will intersect like a small sphere at an even number of points. So if you've like heard the phrase like the 3D color code is transversal CCZ, I think this is like the exact same thing that's going on here. And this is, I guess, one way you could prove that. And so the question now is how do we improve beyond the 3D toric code parameters, which are still quite bad. They're worse than like a classical repetition code. They have like dimension 1 and distance n to the 1/3. Great. So far we have transversal CCZ on the 3D toric code. And this is actually very, maybe even exactly analogous to the state of the literature on quantum LDPC codes, where we forget about CCZ, but just look at getting good dimension distance before roughly like 2009, as far as I'm aware. I guess I wasn't in the field at this time, but this is my understanding. Like I think back then the 2D toric code in a lot of parameter regimes, not all regimes, but a lot of them, was close to state of the art. And people ultimately found out how to improve this by generalizing key properties of the toric code to more exotic topological spaces, things that are not just obtained by tiling manifolds. And these exotic topological spaces were specifically constructed by taking classical LDPC codes and then taking products of them to get higher dimensional topological spaces. So as far as I'm aware, kind of the first instance of this was maybe the hypergraph product codes by Tillich and Zamor, which are just tensor products of classical LDPC codes. And then this beautiful line of work recently kind of improved parameters all the way up to getting these asymptotically good quantum LDPC codes. So what we're doing now is we're doing the same thing, like I guess many years later, but for QLDPC codes with transversal CCZ. Or we're like adding a cup product into the picture. And unfortunately, though, I guess from more, I guess maybe it's a good thing or bad thing depending on how you look at it, we're still kind of in the middle of this. We're not yet at the asymptotically good constructions. With CCZ, we're like somewhere between like the toric code and getting something really good. So there's still a lot of room for improvement. Yes?
Maybe I should have asked this question earlier. I was under the impression of this Easton-Camille theorem, right, that said that you can't have a universal transversal gate set. I don't actually know the details of the theorem. So if you have the transversal CCZ gate, which gate is now missing?
Yep. It will usually be a Hadamard.
Okay. And how scary is that?
Yeah.
That's my favorite game.
I think it's a lot less scary. So I think there's a couple different things you can do. Maybe the most common things are like gate teleportation and code switching. Gate teleportation for Hadamard is not that hard because the state you need to teleport a Hadamard gate is like the plus state. So if you have any code where you can prepare a plus state, then you can teleport in a Hadamard gate. Of course, this isn't, yeah, so this requires some side classical computation. If you want to get rid of that, maybe you want to use something like code switching. But again, then you're switching between a code that has like a Hadamard gate and a CCZ gate. And it's generally easier to find codes with Hadamard gates. So if you have a code with CCZ, it's more likely that you can like find another code with Hadamard than vice versa. But yeah, thanks. I'm like totally glossing over where these codes fit into a larger fault tolerance scheme. Okay, so another option is to actually just use these codes for magic state distillation, and then you can just teleport in the CCZ states into like any other fault tolerance scheme.
How do people do code switching? That wouldn't be transversal.
Yes. So like for toric codes, there's known ways to do it. I think it's less clear what to do for other LDPC codes. I think there's some proposals out there, but yeah, I think there's probably nothing. You probably have to look at like a specific code family to try to work it out.
How do I see that the conditions for this transversal CCZ that you just said is incompatible with those for transversal Hadamard, for example?
Yeah, so I don't know how to prove it in general, except for the fact that Easton-Camille says it must be false.
U2, unitary group, tensor unitary group is not effectively dense in the three-dimensional unitary space.
Okay, but just reasoning from those conditions for the transversal CCZ, it's not obvious how to see that Hadamard cannot be done.
Won't be able to get a dense set, so you won't be able to get all the points.
Yeah. Yeah, I think I agree. Yeah, maybe, I don't know, maybe we can take this offline. Yeah, I'm not sure exactly how to prove it directly, but Easton-Camille definitely does imply it.
Yeah.
And at an intuitive level, like, to get the CCZ, we really want, like, qubits. If you look like the toric code or the constructions we're going to get, we have some like, code chain complex of length at least 3, and we're going to want to put qubits at, like, level 1 of this length 3 chain complex. So transversal Hadamard would flip it up to level 2, which would kind of change the code. So you can see it intuitively that way, but that's not like a formal proof. Great. So I will now describe how we do this in a bit more detail. I need a bit of machinery on code chain complexes. So these are like an algebraic description of topological spaces that abstract away either the key like algebraic properties or in the context of this talk, the key coding theoretic properties. And formally, you can write down like a cochain complex corresponding to a t-dimensional topological space as just a sequence of t+1 vector spaces over F2 with these co-boundary maps delta naught through delta t-1 between them, such that if we multiply together any two consecutive co-boundary maps, we get 0. And the intuition here is that each of these vector spaces Ci corresponds to the set of functions from I-dimensional faces of some topological, like cellular complex, some topological space to F2. And each delta I is the incidence map between I and I+1 dimensional faces. So just to give the example of the toric code again, here this is 2-dimensional, so t equals 2. C0 corresponds to labelings of the vertices with elements of F2. C1 corresponds to labelings of edges with elements of F2. And C2 corresponds to labelings of squares or faces with elements of F2. And we can say that if we start at any vertex, say take the indicator function for this vertex, it's incident to 4 edges, so when we apply delta 0, we get the indicator function for these 4 edges. And then when we apply delta 1, we get, what do we get? So there's 4 faces here. There's this face, this face, this face, and this face. Each of these 4 faces is incident to exactly 2 of the edges that we had. And since we're over F2, that this 2 equals 0. So essentially when we apply delta 0 and then delta 1, everything cancels and we get 0. So we've just seen that delta 0 times delta 1 equals 0. And this cochain complex, such a cochain complex of dimension at least 2, will always define a CSS code where we set QZ to be the kernel of delta 1 and QX to be the kernel of delta 0 naught. And the CSS orthogonality condition is actually equivalent to the cochain complex condition that delta 0, delta 1 equals 0. So then the cup product is the final missing piece here. It's an operation on cochain complexes that abstracts out transversal CCZ. Great, so what is a cup product? For the purpose of this talk, a cup product will be a bilinear map that takes as input a cochain or an element of a cochain complex A, an element of a cochain complex B, and maps out an element of some third cochain complex, which I'll denote by A star B. A and B could be the same or different. They also could be the same or different as A star B. Later we'll kind of instantiate these with specific cochain complexes. But for now you can just think of these as some 3 arbitrary cochain complexes. And you can see that this cup product will always take level I cochains in A, level J cochains in B, and map it to level I plus J cochains in this product complex. So a cup product is actually any bilinear map of this form that satisfies just this single key property, at least for the purpose of this talk, called like the Leibniz rule. And this is the, this may be familiar from like calculus, like just the differentiation rule. It just says that the co-boundary of A cup B is equal to the co-boundary of A cup B plus the co-boundary of, plus A cup, the co-boundary of B. And this should hold for all A and all B. So the intuition here is that the cup product computes intersections or products, like computes products of cocycles or computes intersections of the supports of cocycles. And just to draw out the example again with the 2D toric code, where now A, B, and A star B are all the 2D toric code, then we can try to take the cup product of like cocycles corresponding to like intuitively to this cycle A and this cycle B. And for technical reasons, when we talk about cup products, we need to pass to like, I've been saying co a lot, we need to pass to like cocycles instead of cycles. So the cocycle corresponding to like this cycle A is basically just a cycle, but instead of like taking just a smooth like path like we did before, we take like the dual path, which is like this ladder type path going around the torus. And the same thing for B, we take like a ladder type cycle instead of just taking like a true cycle. This is like, I guess, Poincare duality or something. But you can, if you just kind of squint and don't look too closely, this is still just two cycles that we're intersecting. And indeed, A cup B is going to be just the indicator function for this single square lying at the intersection of the cycles A and B. So this cup product on the toric code or on manifolds is really just computing intersections of cocycles. Great, so why does the cup product imply a transversal CCZ gate? So the key lemma here is that for any cochain complexes A, B, and C with a cup product, and then for any element Z lying in the kernel of the transpose of the level 2 coboundary map of the product complex, then we have a trilinear form that simply maps A, B, C to A cup B cup C dotted with Z. And this trilinear form is QX perp invariant, where we've placed qubits at like level 1 of our cochain complex, so QX perp is the image of delta naught. So sorry, this is a bit technical. The high-level overview here, or the high-level takeaway here is that the cup product is already some trilinear form that has naturally, by the Leibniz rule, has some invariance properties. And this is basically exactly what we want for transversal CCZ. So assuming that this cup product leads to a constant depth physical circuit, which in all the instances we'll talk about it does, then we get transversal CCZ from the cup product. And as I just mentioned, the proof of this key lemma is really simple. It's just an application of the Leibniz rule. It's literally like a 2-line proof. We just kind of take any like cochains A, B, and C. We take their cup product and apply the coboundary map. And then we get out the coboundary of A, cup B, cup C. So that means that kind of coboundary of A, cup B, cup C is in the image of delta 2. And since Z is in the kernel of delta 2 transpose, that means that Z dotted with coboundary of A, cup B, cup C is 0. So we get QX perp invariance. So I guess that was a bit quick, but you can go through this on your own time. It really is just a direct consequence of the Leibniz rule. Great. So I guess takeaway here is Leibniz rule implies that cup product gives transversal CCZ. So now we've reduced our goal to constructing quantum codes from cochain complexes with a cup product. And now we go back to the Tillich-Seymour paradigm from 2009, where the key idea is to construct quantum codes by first constructing desirable one-dimensional cochain complexes using classical LDPC codes, and then extending these one-dimensional complexes to higher dimensions using tensor products, which they called hypergraph products. So specifically in our setting, we want like a triple of one-dimensional cochain complexes arising from like large distance classical LDPC codes that also have a cup product. And then we'll just take like the tensor product of kind of three of these complexes, and we'll get like three-dimensional cochain complexes that together have a cup product between them, which will give us a transversal CCZ across the quantum codes associated to these three cochain complexes. Now I haven't actually defined what like this tensor product is of cochain complexes. For the purpose of this talk, it's like a standard operation. It's kind of the algebraic version of taking like a Cartesian product of topological spaces. So for the purpose of this talk, I'll gloss over that, and instead, just for the purpose of time, I'll focus on constructing these one-dimensional complexes. And then you can trust me that we can actually then just kind of use known products to get up to three-dimensional complexes. And this tensor product commutes with a cup product, which is why we're able to just focus on the one-dimensional case. And then and getting cup product for the one-dimensional case, and then that induces a cup product on the three-dimensional case. This was a nice observation in Nico's paper. And also, as pointed out in Nico's paper, we can generalize this tensor product to what's called like a balanced or a lifted product in the literature, which makes it more difficult to analyze distance, but also lets us potentially get higher distance codes than we can just get from tensor products. Great, so we've kind of reduced our whole problem of constructing quantum codes with transversal CCZ down to just the problem of constructing one-dimensional cochain complexes with a cup product from classical LDPC codes. So how do we normally construct classical LDPC codes? Kind of one of the most standard ways is like Sipser-Spielmann paradigm, where we have some expander graph, like a constant degree, say D regular expander graph, and we impose some local code A on this expander graph. Meaning that we write down a one-dimensional cochain complex where at level 0, we just have assignments of elements, oh sorry, that C should be an A here, an A there. We have assignments of the local code to vertices, and then assignments of bits to edges. And the co-boundary map just kind of does the natural thing. If we have some level 0 cochain, which just is a local code word at some vertex, the co-boundary map just maps the bits in this local code word to the edges incident to that vertex. It just kind of spits out the bits in the local code word. And it was shown by like Sipser and Spielmann that if the graph G has good expansion and both A and its dual code have good distance, then the classical LDPC code given by the kernel of this co-boundary map has good distance. And the real key lemma for what we want to do, which was, I guess in this version it was shown by like David Lin in his paper last year, is that for a pair of local codes A and B, there's always a cup product between the one-dimensional cochain complexes we get from this expander graph using local codes A and B respectively. And this cup product outputs an element of the cochain complex corresponding to the same expander graph, but now with the product local code. Where by product local code, I just mean the component-wise product of A and B. So I guess just to repeat, this lemma is saying that we can always get a cup product on one-dimensional cochain complexes from these classical LDPC codes. It's just that the cup product starts with classical LDPC codes with local codes A and B respectively, then outputs something corresponding to the classical LDPC code with local code A star B, where A star B is just the component-wise product of A and B. So this is really the key lemma. It really lets us do everything, and yet, at least in this one-dimensional case, the proof is super simple. We literally just like define the cup product to take component-wise products of the cochains, like of the vectors. So for taking and we of course want to check that this satisfies the Leibniz rule. If we take the cup product of like two zero-dimensional cochains or like one-dimensional cochains, it's super easy to check this. So there's kind of like one thing you have to decide, which is like when you take the cup product of a 0 cochain and a 1 cochain, that means like you want to kind of multiply the local code at a vertex with like the assignment on an edge, and you need to decide like which of the two vertices to choose. You just do it according to some global ordering, and it all works out. But all that being said, kind of this lemma, it's a really simple proof, but it's kind of the key. It's telling us exactly what we need to get a cup product. Great, so how do we choose the local codes? So we want classical LDPC codes where kind of their component-wise product of their local codes, like A star B star C, is non-trivial. It's not the entire vector space. Because intuitively that corresponds to making sure that the output of this cup product is not kind of a trivial LDPC code. Now is where we really run into a problem, because it's notoriously hard to construct good classical LDPC codes where the local codes have a multiplication property. The multiplication property is typically only satisfied by like either the repetition code, or like algebraic codes such as like Reed-Solomon or algebraic geometry, these codes arising from evaluations of polynomials. But LDPC codes with these types of local codes typically have very low dimension. So there's kind of this like well-known challenge of like constructing these LDPC codes with the multiplication property of the local codes. And this is kind of why we don't yet have like asymptotically good construction. This is where the whole challenge lies in like choosing these local codes with a multiplication property. So what's known? Like, what are the known constructions? Of course, we could just take all three local codes to be a repetition code, so the product is also a repetition code. That's literally just giving us the 3D surface code. We could take all three local codes to be a Reed-Solomon code, so the product code is also a Reed-Solomon code. And that gives us these codes that we constructed with David Lin that I mentioned at the start. And actually, to achieve good dimension here, we need to choose a very special spectral expander. Our spectral expander G has to be based on like some sparsification of a Reed-Muller code, and it interacts very well with these local Reed-Solomon codes. So kind of by very carefully choosing the graph G, we can get decent dimension for these codes. And as far as I know, this is like the only known construction that kind of beats classical repetition code parameters. So it's like k times d greater than n, and as a result, we're able to also do like low overhead magic state distillation with these codes. And then the final construction is Guan Yu's construction, which is very clever. It somehow avoids using an algebraic local code. And what he does is he chooses A to be a random code, or just some good code, B to be the dual of A, and C to be just a repetition code. And the observation here is that if you take anything in A, anything in B, and anything in C and multiply them component-wise, and then sum up the entries, you have to get 0, because A and B are dual, and C is a repetition code.
But Guan Yu's construction is not addressable, right? Because it's among big blocks.
Yep. Yeah, exactly.
But I guess here your point is that your construction is addressable within the same block.
Oh yeah, yeah, it is. Yeah, it's a good point, thanks. Yeah, so this one, because he's like playing these clever tricks, yeah, he doesn't get like addressability. He can't generalize to like CC, CZ with the same parameters. Whereas ours does, I think, generalize a bit easier. But Guan Yu also, to get these parameters, he like sticks in a balance product. One of these two tensor products he uses as a balance product instead. And so that's how he gets distance n to the 1/2, which is better than any of the other constructions. Great. So now to wrap up, I'll just highlight some challenges for further improvements. So what we really want to do is beat the classical repetition code parameters. And I think this probably requires using algebraic local codes. I'm not 100% sure, of course. I don't know a proof of this. But it really seems to run this challenge that we have of like getting algebraic local codes, have the multiplication property, and also wanting low weight checks and large distance just seems really difficult. And we were able to get around this problem to some extent by just carefully choosing everything to gel together, kind of making sure our local codes and our expander come from like a very unified construction that arises from like this classical Reed-Muller code. And actually, if we take our construction and like replace the tensor product with the balance product, we get a candidate construction with like almost linear dimension, almost linear distance, and so forth. But we don't know how to bound the distance because these algebraic local codes are much more difficult to analyze than like the random local codes that are typically used in these like good or almost good quantum LDPC codes. So I now just want to highlight one other potential stepping stone, which is actually the classical analog of this problem. It's kind of interesting that like when people were trying to construct good quantum LDPC codes, we always had good classical LDPC codes. So it was always a matter of like getting something quantumly that we had classically. In this problem, we actually do not have good classical codes with the analog of CCZ, which is just with this multiplication property. So it's like a wide open question to construct good classical LDPC codes with a multiplication property. I believe it's probably a prerequisite to getting good quantum LDPC codes with CCZ. And the current state of the art are like classical Reed-Muller codes arising from evaluations of multivariate polynomials, which are not far. Like they have almost linear distance, linear dimension, and polylog check weight. But they're still not asymptotically good. And we can view our construction as giving a quantum analog, but of course with worse parameters right now. And I'll just add one more piece of speculation, which is that kind of probabilistically checkable proofs seem to be, like, they also seem to arise from these algebraic codes with like local checks, typically with like some sort of multiplication property. And I don't know too much about this, but my understanding is there's like this problem out there of whether we can have like linear-sized classical probabilistically checkable proofs. And this seems like closely related to the problem of getting asymptotically good classical LDPC codes with a multiplication property. Like maybe this coding theoretic question is a prereq to getting linear-sized BCPs. Okay, so I'll just wrap up. I talked about transversal or quantum LDPC codes with transversal CCZ. These are motivated by critical bottlenecks in quantum fault tolerance. Getting good parameters is asymptotically optimal parameters is still wide open. And despite the like practical motivation, this question also has a really nice interpretation from topology. So I'll wrap up there. Thanks.
Given that you've talked about intersection, have you seen tessellations of, let's say, RP3, because that has a complete intersection in itself? Have people, would that be a or is that studied as possible ways to tessellate, let's say, RP3 or even possibly RP4 rather, because you can take two hyperplanes and you intersect them transversely, then you should get RP2 in some way. So,
yeah,
do tessellations like that, or, you know, would that be, is that something which is studied?
Yeah, so I think this has been studied. I think actually with some of these things you can get even crazier gates than CCZ. I think actually Guanyu Zhu, who like one of his papers I was talking about, I think he has another paper, I forget the other co-authors, but I think they studied like these exact manifolds you're talking about, and they got some like transversal like small angle rotation, so kind of things like higher up in the Clifford hierarchy and like single qubit gates. So yeah, so I think that people have studied this, but I'm not familiar with exactly what the results are.
I think you mentioned that that code you proposed was well suited for distilling like magic states, maybe CCZ states. Why do you say that's the case? I don't know if you justified it and I missed it.
Sorry, which code was the?
You have this code with n to the 1 minus epsilon.
Yeah. So I think that was just the like standard magic state distillation protocol has an overhead that's measured by this number gamma, like log n over k over log d. It's kind of like you do you kind of like prepare the code, do transversal CCZ with teleportation, you distill out a smaller number, and then you like repeat. So if you just run like the standard magic state distillation protocol with these codes, you get gamma going to 0, which means you get like a sub-logarithmic overhead in terms of the ratio of like noisy states that you start with to like high-quality distilled states. So yeah, that's all I was saying there. I guess the LDPC property is also nice because it means that when you're like measuring out the stabilizers during distillation, you're only measuring these low weight checks, whereas a lot of codes that have been proposed for magic state distillation have like high weight checks, which take more time to measure. So yeah, so I think all I was really saying is like they get this gamma going to 0.
So you're saying that this cup product kind of implies that you have transversal CCZ. So I suppose that's a sufficient condition. Is it also necessary?
No, that's a great question. Yeah, I've thought about this, and I think the answer is no, in the sense of you can write down some quantum codes with transversal CCZ that don't seem to have a cup product.
I see.
For instance, like we have constructions of asymptotically good quantum codes, but that are not LDPC, that have transversal CCZ. And if you try to, at least I've tried to extract a cup product out of them and couldn't do it. maybe there's a way to do it, but I think the answer is no.
Thanks.
During the talk, there seems to be a trade-off between Hadamard and CCZ. Suppose I completely ignore CCZ, and will I have addressable transversal Hadamard and all the other basic gates?
So addressable Hadamard is tricky.
So that's just almost a no-go thing.
Yeah, so I don't want to say it's like impossible, because you could always imagine schemes where like you do, like you take whatever qubits you want to perform a like Hadamard on, maybe like take them out of your code into another code and then do some transversal Hadamard and put them back in. But that's like some constant depth circuit. Maybe there's like some code switching there. If you just want a single code with addressable transversal Hadamard, I've never seen something that can do that.
So in your opinion, actually Hadamard is one of the hardest things?
No, I think CCZ is still, I think so Hadamard is easy transversally. And I think addressability maybe, I think if you have some fault tolerant scheme, like the thing I just said, where like really you just need the ability to like kind of extract qubits from a code block. And I think kind of things like CCZ will probably be more helpful for that than Hadamard. Like with CCZ, that also gives you Toffoli. And with Toffoli, you can do like controlled swap, for instance, which in controlled swap could be really helpful for like extracting qubits if you then want to do like any controlled gate.
Thanks.
But this is also just from an asymptotic perspective. From a practical perspective, I'm not trying to make any claims.
And I guess you kind of mentioned like 3 methods, like magic state distillation, code switching, gate teleportation. How would you kind of compare them? Like, say you have a good code with parameters that has the transversal CCZ, like, is it better to do most of your computations in this code rather than like a smart code that can do?
Oh yeah, no, that's a great question. I think from practical considerations, I'm not sure. It probably depends on like your hardware platform. Yeah, it's probably pretty hardware dependent. It seems like people are generally leaning towards preparing magic states, maybe distilling them or just preparing them separately, then teleporting them in. But it might just be because we don't have good enough codes with transversal CCZ yet. I think if you could imagine if we had really good like codes with transversal CCZ, you might just want to do all your computation in the base LDPC code and save yourself like the concatenation that comes with magic state distillation. So yeah, so I think it's unclear.
Last question. Okay, great. Thank you. Last talk tomorrow is quantum chemistry. First talk's at 9:30.